Awesome. So 4 has f of x and y, and that is 3 to the x plus 7xy. And they're asking us to just choose one. They're all the same. You want f of 0 comma negative 2, f of negative 2 comma 1, or f of 2 comma 1. You choose. It doesn't matter. F of
0 comma negative 2.
0 comma negative 2. That's all I need to do. So replace x by 0 and replace y by negative 2. But 0 times negative 2 times 7, this is 0. And 3 to 0 is 1. Done. In 6.1, we only want to evaluate functions of several variables. But also we want to talk about the domain. So I want to look at, let's say, problem 10. I have k of x comma y. They're getting innovative here. 1 over x plus y over x minus 1. Okay. Now when I write a domain for such a function, I have to write the ordered pair x comma y such as, or having the property something follows. Well, I'm looking at this. Y is okay for any y, I don't care, but x cannot be 0 and x cannot be 1. So x cannot be 0 and 1, which means, and you can write if you want, y anything. We don't do that, but if I don't mention anything about y, it means that y can be anything. This is how I write the domain of such a function. So function k with x of x comma y has ordered pairs, not x, but x comma y, having the property that y, it has no restriction, but x cannot be 0 and x cannot be 1. Let's look at one more. I don't know, this one, 11. We have f of x comma y is the square root of y minus 3x. We discussed the square root many, many times. What is the condition that you will have to write?
Greater than 0.
Yes, but what? Greater than or equal to 0, but what?
Y minus 3x.
Y minus 3x. That's it. That's our domain. The ordered pair having the property that y minus 3x has to be greater than or equal to 0. Done. That is it. Now,
This is so easy.
I know. I know. I just want to look now the last two sections of the class. I'm on page 8, 6.2 and 6.3. Derivatives and max-min for functions of two variables. I know you couldn't see what I was writing, sorry. So in 6.2 and 6.3, we're going to talk about the derivatives of these functions of two variables and how to find max-min for them. And this is going to be the end of the course. No more new material after this. Hopefully we can finish it tonight. If not, I'll need a few minutes on Monday. Of course, Tuesday, Mondays and Wednesdays and Tuesdays are okay. So I want to be on page 566. Okay, so we're going to choose a function. Let's choose a function. Yes, of course, they are as complicated as possible. Okay, I'm going to choose something simple. I'm not going to answer this just yet. So I'm just going to choose a function. So f of x comma y equals 3x squared y minus 2xy plus 4y. Before we continue, I just want to show you how these look like, because this is now in 3 dimension. What do I mean by 3 dimension? This is what I mean by 3 dimension. So this is x, this is y, this is x, this is y, and this is the function up here. So this is going to be a surface. This is not going to be a function like we had. It's a function, but it's not a function of one variable which can be graphed like this, right, on the Cartesian system. We need a 3-dimensional Cartesian system now. So I just wanted to show you, we're not going to do anything with this, but I just want you to see how a function like that looks like. Because I like their graphs. Their graphs are really nice. Here it is. See, x, y, z. So this is how it looks like. It's a surface. Okay? Good. So what happens here is, remember when we had a function like, let's say 2x plus 4, we wrote dy over dx as being 2, or f prime of x, or y prime. So please keep this in mind. This letter, normal d, refers to a function of one variable. If I want to differentiate a function of 2 or more variables, but we're only looking at 2 variables. If I want to differentiate a function of 2 variables, I can only differentiate with respect to x, keeping y fixed, like constant. And that is called fx. If I want to differentiate with respect to y, I have to keep x fixed or constant. The notation will not be a regular d, but the notation will be this f, this x. This is called partial. Why partial? Because I'm differentiating with respect to x when y is fixed. It's partial derivative, not derivative, partial derivative. And the symbol is not dy over dx or df over dx, which is specific for one variable, but it's the round d, or just write fx. So one more time here. Fx is the same with the first partial derivative of f with respect to x. This symbol signifies the fact that f is not a function of x only, but it's a function of x and another variable, in this case y. So fy is the partial derivative of f with respect to y. Also, I can differentiate this twice with respect to x. So that will be fxx, which means the second derivative, partial derivative of f with respect to x twice. We do not need to use this notation. We need to know what it means. Also, I can differentiate the function f with respect to x and then with respect to y. I can differentiate f with respect to y and then with respect to x. So basically what we have here in general, partial derivatives, fx fy, first order, fxx, fyy, fxy, fyx. This is it. First order, meaning the first partial derivatives. Second order partial derivative, second order partial derivative, second order partial derivative, second order partial derivative. These should be the same. So let's illustrate and find all of them. The first order, second order for this function. I'm going to copy it again. It sounds difficult. I hope you're not going to find it difficult in a minute. Okay. So if I want to find fx, it means that I consider y a constant. I ignore it completely. So I differentiate with respect to x. So I have 6x y. I differentiate with respect to x. I get negative 2 y. I differentiate with respect to x. There is no x. If there is no x, this is a constant. When I differentiate it, what do I get?
0.
That's it. Done. Now I want to differentiate this with respect to y. X is constant.
Can you repeat that again real quick?
Yes.
4?
From the beginning, this one,
No, the 4y.
it doesn't have x. It's a constant.
Okay. So then that multiplies by the y?
It's constant. Y is constant. That's why I covered it.
Okay.
When I differentiate this, because it's a constant, I get 0. Now I differentiate with respect to y. X is constant. And there is no x there. I differentiate 3 blah, whatever number, y prime. So it's that number. Here I have negative 2y. When I differentiate negative 2y, I get negative 2 and that number. When I differentiate 4y, because I differentiate with respect to y, I get 4. Let's continue with fxx. So y is constant. When I differentiate 6x blah 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 with respect to x, I get 6y. When I differentiate this with respect to x, what do I get? Nothing. That's the answer. Awesome. Now let's find fyy. I'm differentiating this with respect to y. What do I get? There is no y.
No, nothing.
Nothing. Awesome. Finally, fxy. I have fx. Now I want to differentiate with respect to y. Can anyone tell us? I differentiate this with respect to y and this with respect to y. What do I write? When I differentiate y, I get 1. So I have 6x. When I differentiate this with respect to y, what do I get?
-2.
That's it. Good. So one more, which has to be identical with this. fyx. So I have fy. Can anyone differentiate this with respect to x for us?
X. 6x minus 2.
They have to be the same. Yes. That's it. I know one example is not enough, so let's choose another. Yes, it can get complicated. Page 567. It can get complicated because, of course, when we start looking into, I didn't press enter. When we start looking into functions like these, yes, it starts getting complicated. So let's choose another. Which one?
18.
This one. Very good. So let's look at 18. So this is page 10, 18, 18, 18. Okay. fxy equals x over y plus y over 5x. So we want to determine all four. So fx, when I differentiate with respect to x, x prime is 1, but I still have 1 over y. Plus, now careful, because now x is in the denominator, so I have 5, I didn't mean that. I have y over 5 times 1 over x. So y over 5 has to stay. It's the constant in front. But when I differentiate 1 over x, I hope everyone remembers is negative 1 over x squared. So when I differentiate the first piece is nothing else but 1 over y times x. When I differentiate this with respect to x, I get 1 over y. When I differentiate this one, y over 5 times 1 over x, I have to copy the constant in front, and I have to differentiate 1 over x, which is this. So then fx equals 1 over y minus y over 5x squared. Now, I hope they're not asking for more than just the first order on this, because they're, okay, oh, good, because second order will be pulling our hair. Okay, good. So now fy. Now this is x over 1 over y. So when I differentiate with respect to y, I have x negative 1 over y squared. Now this is easy, but when I differentiate with respect to y, I get plus 1 over 5x. I know I only have 3 minutes left from today. I just want to explain something, and I'll stop as I have to in 3 minutes, I promise. Okay. Which is the last section, which is 6.3. How to find the max min of such a function of f of x comma y. How do I find that? There is a procedure. It's called the D test. So I will not have time to illustrate the whole thing, but I just want to choose an example and just start it. And that's on page 576. 576. I promise to stop in 2 minutes. Okay, so find the relative max or min value. I'm going to just choose a function like, let's say, I don't know, 5, in which we have f of x comma y equals x cubed plus y cubed minus 3xy. Okay, so what we have to fill in and determine is something called the D test. And the D test is this. D equals fxx of a comma b, and I'll have to explain what a comma b means, fyy of a comma b minus fxy of a comma b squared. We calculate this and we will draw some conclusions. What is a comma b? And I'll stop after I mention what a comma b is. It's a point, of course. and the point is determined exactly like we did for functions of one variable. So the a comma b is the solution of the system fx equals 0 by critical numbers and fy equals 0. And once we determine solution or solutions, they can also be solutions of the system. So we determine fx, we set it equal to 0. We determine fy for that function, we set it equal to 0. We get points or point, and then we plug this in, and I'll tell you what we need to do with that value. And that's the